In this video, we will look at redox reactions. In order to actually look at a redox reaction, which is basically a split, it's split into oxidation half reaction and a reduction half reaction. In order to actually look and determine which one is oxidation and which one is reduction, we have to calculate the oxidation number. Another thing that could potentially confusing for a lot of students is the nomenclature, the actual definitions. So an oxidizing agent is actually something that gets reduced. So as an oxidizing agent, I am the agent that causes your oxidation. In turn, I get reduced. A reducing agent is something that gets oxidized. So I am a reducing agent. I am the one that causes your reduction, and in turn I get oxidized. So the reducing agent is the chemical that gets oxidized, causing your reduction. Remember, these are all couples. You need a couple. An oxidation agent is something that gets reduced, causing your oxidation. So having said that, in order to solve this problem, we need to split this into an oxidation reaction and a reduction half reaction. In doing so, we're going to calculate the oxidation numbers. Remember, we lose electrons oxidation, you gain electrons reduction. So let's calculate the oxidation number here for Fe. That is a single lone element, so that's going to be 0. Oxygen is a single lone element, even though it's O2, that's going to be 0. The Fe2O3, the iron 3 hydroxide, the oxygen has a different oxidation number, as well as the iron. So let's go ahead and rewrite this and do this properly. All right, as stated before, the oxidation number of iron here is going to be 0 because it's totally by itself, it's a loner. The oxidation number of the oxygen, O2, is going to be 0. Fe2O3, we can actually deconvolute this. This is actually formed by Fe plus 3, and O will always be minus 2. So the oxygen here has an oxidation number of minus 2. Okay, I'm talking about the oxygen. And the Fe has an oxidation number of plus 3. I'm talking about the iron. So let's go ahead and write down the oxidation states as they have changed or transformed to do this reaction. We have one half reaction where Fe is going to go to Fe plus 3. All right. See, Fe with an oxidation number of 0 is going to an Fe plus 3 in the oxidation state. We're going to balance that. So we balance that with electrons. So this will be balanced with 3 electrons. So the charge here is 0. Plus 3 plus a minus 3 is 0. So here we have 3 electrons lost. The way you want to think about this is that iron, in order to become iron plus 3, lost 3 electrons. And remembering Leo Gurr, losing 3 electrons is oxidation. So this is an oxidation half reaction. Okay. Along the same vein, let's look at oxygen O2. We know that it has a lone element and oxidation number of 0. This oxygen here, okay, in forming Fe2O3 became minus 2. So one thing we want to do is we have 2 oxygens here. We got only 1 mole of oxygen here. So we will balance that accordingly. So now we will balance electron-wise charge. So we got minus 4 here. I'm going to put a 4e minus here. And when I put a 4e minus, I come to the realization that in order for O2 to become O minus 2, I put a 2 here to balance the oxygen atoms. In order for O2 to become O minus 2, I have to gain 4 electrons. So when I gain 4 electrons, this is reduction. Right? So Fe is undergoing oxidation, so it is the reducing agent. O2 is undergoing reduction, so it is the oxidizing agent. And this is how we split apart this 2 reaction into the reducing agent and an oxidizing agent. All right, let's continue on with part B here. Cl2 plus 2 sodium bromide goes to 2NaCl plus Br2. So we know here Cl2 has an oxidation number of 0, it's standalone. Cl here in the compound sodium chloride has an oxidation number of minus 1. So we're going from 0 to minus 1. Here sodium is plus 1, and sodium is plus 1 here. Again, ionic compounds, group 1 elements, we're going to be plus 1. The Br is minus 1 oxidation state here in this ionic compound. In Br2 standalone, it's actually 0. So we have a Cl2 going to a Cl minus, and a Br going to a Br2. The Na plus goes to Na plus. The oxidation state, nothing is happening to the Na plus, it's just staying the same at +1. So let's go ahead and rewrite this. All right, as stated before, the oxidation number of Cl and Cl2 is 0. The oxidation number of NaBr of Na and sodium bromide is +1. The oxidation number of Br is -1. That's how you form sodium bromide. The oxidation number here in Br2 is standalone 0. So we have Br minus going to Br2. And then we have Cl2, which has an oxidation number of 0, going to an oxidation state of -1, Cl minus. Okay, because remember, sodium chloride Na is +1, Cl is -1. So these are the two states that we split to get this redox reaction. Let's go ahead and individually balance. One is oxidation, one is reduction. Let's go ahead and individually balance these. First things first, let's balance the element Br2, so that becomes 2Br. Now we balance the charge. -2 here, I'm going to put 2 electrons here to get a -2 on the on the product side. So in order for Br minus to go to Br2, it loses 2 electrons. Again, the key point here is Leo Gur. Electrons are being produced, they are being lost in the form of products. So Br minus loses 2 electrons to become Br2. Losing an electron is an oxidation half reaction, so this is an oxidation half reaction. But in terms of agents, the Br minus is a reducing agent. So we have an oxidation half reaction. This reactant is the reducing agent. So Cl2 going to Cl minus. Let's go ahead and balance the Cl atom. I got a -2 here. Let me put a 2E minus here on the reactant side. So -2, I am charge balanced. In order for Cl2 to become Cl minus, it has to gain 2 electrons. Let me repeat that again. Cl2 obtains or gains 2 electrons and in turn becomes Cl minus, 2 moles of Cl minus. Gaining 2 electrons, that's reduction. And something that undergoes reduction implies that Cl2 is the oxidizing agent. That is to say that Cl2 oxidizes Br minus to Br2, and when it oxidizes this to that, it itself gets reduced to Cl minus. Alright, silicon plus 2F2 goes to silicon tetrafluoride. This has a charge of 0. F2 has a charge of 0, but this is kind of a weird one because silicon actually is kind of on the wall between ionic and covalent because silicon is a metalloid. So even though silicon tetrafluoride is covalent, it does have an oxidation state. The oxidation state of Si is going to be +4. The oxidation state of F is going to be -1. If you have to remember, F in a compound will always have an oxidation state of -1. F alone by itself, standalone, will obviously, just like all the other elements by itself, without a charge, will have an oxidation number of 0. So let's go ahead and rewrite this and figure out the two reactions, half reactions. Alright, as we stated before, silicon has an oxidation number of 0, and Si will have an oxidation number of +4. Okay, this is a little bit tricky from what we've been kind of teaching you before. Even though this is, for practical purposes, covalent, in a redox reaction we're going to have to assume this has a charge. And fluorine in a compound will always have a -1 oxidation state. So here we have Si going to Si +4. Okay, remember, fluorine, when it's bound to any compound, ionic or covalent, will have an oxidation number of -1 for fluorine. And this definitely has an oxidation state of 0. And F in a compound will have an oxidation number of -1, as alluded to before. So let's go ahead and balance this. So for silicon to go to Si +4, it loses 4 electrons. So losing 4 electrons is oxidation. So this is a oxidizing half reaction or oxidation half reaction. Silicon in turn becomes the reducing agent. Because silicon gets oxidized, it causes the reduction of F2 to F minus. Let's go ahead and balance the F's here. I got a -2 here, and I'm going to add 2 electrons to balance out the minus charges. So -2 on the reactant side, -2 on the product side, and we gain 2 electrons. So this is a reduction half reaction. And fluorine, F2 diatomic, gains 2 electrons. By gaining 2 electrons, it helps oxidize Si to Si plus 4. So this is the oxidizing agent. Our final problem here in this example set is hydrogen plus chlorine goes to 2HCl. Hydrogen standalone is 0. Chlorine standalone is 0. Hydrogen and hydrogen chloride or hydrochloric acid, H is +1, Cl is -1. See, that's how we form HCl. +1 with H reacts with the -1 of Cl. We do the switcheroo, we get HCl. And we can avoid the 2 just for now. Let's split this into the reduction half reaction and the oxidation half reaction. Alright, so H2 has an oxidation number of 0 because it's a standalone element. Cl in Cl2 is by itself all alone, no charge associated with it, so it has an oxidation number of 0. H is +1, Cl is -1, that is how we get HCl. So here we have H2 going to H+, and then we have Cl2 going to Cl-. So let's go ahead and balance the H's here. That's going to be 2 H's, and to balance the charge, I'm going to add 2 electrons here, +2, plus a -2 is 0. So in order for H2 to become 2H+, it loses 2 electrons. So this is an oxidation half reaction. H2 is getting oxidized, and it is causing the reduction of Cl2 to Cl-. So this is also known as the reducing agent. Alright, going now here, for every oxidation there has to be a reduction. Obviously this half reaction has to be a reduction. Balancing out the Cl atom, we have -2 here. To balance out the charge, I'll put a 2 electron there. So -2 balances with the -2. Here the 0 balances out with the 0. And here Cl2 gains 2 electrons. If you gain 2 electrons, that's a reduction. And Cl2 causes the oxidation of H2 to H+, so we'll also call it the oxidizing agent. And that is the answer here. Now let me go ahead and take the next step here. Okay, if we add an oxidation half reaction to a reduction half reaction, okay, you always want to cancel out your electrons. Adding these 2 up, I'm going to get, okay, what I started with, which is H2 plus Cl2 goes to 2H plus 2Cl-. Well, 2H plus 2Cl- is nothing more than 2HCl. So, what I want to illustrate to you here is that, we just basically split this reaction into its oxidation component and its reduction component. If you add those 2 components back together, you automatically get the original reaction.